All right, team, it is time for our focus today, which is completing the rest of our Big E assignment in class today. Should have already completed part 1 yesterday with our diagrams and questions. So our focus today is part 2. Looking to submit today so you don't have to worry about it over the weekend. We do have a homework check on this Monday, so you know what that means. You got to come with this completed and ready to go. So yesterday we spent some time creating 2 elliptical diagrams. An ellipse is of course a fancy space word for oval, right? We're thinking about shapes that are close to a circle but have been elongated. So that is our elliptical shape. So this blue line right here is looking at our ellipse. And when we drew our ellipse yesterday, we had in our diagram 2 foci, 2 focus points, right? And of those 2 focus points, one always needs to be the object that the planet is going around. So in this case here, we have our sun. And then the second focus point is that imaginary, or really better word is mathematical second point that creates the elliptical shape that we see. As that ellipse is then created, this becomes the orbit path for whatever the planet is orbiting that sun. And on that orbit path, there are 2 main points. We had yesterday our aphelion, which is our furthest point that the planet reaches on its path. So we can see here from the sun to aphelion, that would be the farthest away the planet gets within that orbit path. And over here then is our perihelion, our closest point that the object reaches on its orbit path relative to the sun. Okay, so lots of different ways you can think about those terms to remember. We mentioned that one, aphelion is away, the farthest away in that example. So we're going to continue to use these parts as we talk today, highlighting really that distance between the perihelion and the sun and the aphelion and the sun. And so yesterday when we labeled those, we had our distance here, the perihelion, the closer distance, that was our lowercase q. And the distance from aphelion, that was our capital Q. Okay? So the big Q is representing the bigger distance, the farther, the away distance, if you will. And then the little q is the perihelion, the closer distance. So we're running right along that major axis. So looking at your notability, again, we completed part 1 yesterday. So we created our diagrams. You should have those screenshots in here. And we asked you to finish up these questions ready for today. And reminder, there's always these little speaker notes, so you can click on those and get help from me if you're not really sure what that question's asking. But here's what your 2 diagrams are looking like. And we noticed that that foci distance is really determining a couple things in our diagram. It's creating a different shape, right? The closer they are, the more circular that elliptical orbit appears. When they're farther apart, it's just stretched out a little bit more. And these ellipses can be tricky because they do all really look circular. However, there's not an orbit that is a perfect circle. Our focus today in part 2 is this keyword right here. You can highlight along with me, eccentricity. Eccentricity of an ellipse is really looking at how much the orbit deviates from a perfect circle. Okay, so really how circular is the orbit? And we can think about this orbit shape as either being closer to a perfect circle or closer to a more flattened out ellipse. And as you can see here, we are going to be doing some calculations today using those Q variables and just plugging into these 3 very simple formulas, okay? As you calculate these eccentricities, we're going to determine if it's a lower eccentricity, closer to 0, or a higher eccentricity, closer to 1. And again, if it's close to 0, like 0.0, let's say 26, that's going to be a pretty low eccentricity, right? Then we know it's going to be really close to a circular orbit. Not a perfect circle, but close, okay? If it's a higher eccentricity, like a 0.873, that's going to be a very flattened or elongated ellipse. Try to draw one in there with your Notability so you get that little visual, okay? So this is a great spot in your assignment to keep going back to as you're working these eccentricity calculations, to really remind yourself, okay, am I a higher or a lower? Is this more elliptical, stretched out, or is this more circular with that low number? So you'll keep coming back to those highlighted notes, okay? Here's what we're thinking about. You've got your two visuals of your ellipse. Yours are up here a little bit, and that's okay. What we want to do here is calculate the eccentricity. So we're actually going to end up with some decimals here to let us mathematically know how close our orbit is to a circle. Okay? Here was where this demo, I guess, gets a little bit tricky, is everybody drew their own ellipses yesterday in your group. So my numbers might be similar to yours, but they are going to be different. So I'm going to point out where I'm getting my numbers from. I'm going to point out what my numbers are, but I want you to make sure you're using your actual numbers, okay? So if you don't see your diagrams right now, you want to make sure you have those and you're ready to move forward. So ellipse number 1 is our diagram where the foci were only 2 centimeters apart. So that's the one where the foci are closer together. So first thing we're going to do is just record our 2 pieces of data, our 2 variables. And I'm going to try to stick with my 2 colors that match my diagram here. So I'm going to use blue for my small q. For diagram 1, that was the 65 millimeters. Again, I'm just getting that data right from my picture. That's the perihelion distance, the shorter distance, when the sun is the closest to the planet. And then my aphelion distance is kind of that reddish pink here. That's a little bit longer because aphelion is the farthest point. So that's my 85 millimeters, okay? So I've recorded my 2 pieces of data. I have those right here. Now I need to plug into the formula. So this one is just a quick subtraction. So I've got my big, 85, minus my small, 65, and that is going to be my f variable. Then I've got my, again, same 2 numbers, big Q, 85, but this time, whoops, I'm adding them together. And that is going to be my D variable. Go ahead and pause and finish those calculations. And if you haven't pulled a calculator up yet, feel free to go ahead and do that, whether you have one on your desk or on side by side like me. But I'm just plugging in my data, 85, right? So there's my first number. So you should be solving for yours at this point. Okay, so 20 is my F, 150 is the D, right? Simply added 1 and subtracted 1. Now here's my final calculation. F divided by D. So I've got my F number here. That's 20. I'm going to divide that by D, 150. And it does say, show your calculations. That's because I want to make sure you've plugged it in correctly. So 20 divided by 150, and there is my small but very important decimal. Okay, and we're just going to round to the third decimal. So that doesn't mean anything to me quite yet because I do want to compare it with my second ellipse eccentricity. So again, I'm going to do the same thing for now my ellipse number 2. I've got my small q, this time is 35, and my big Q, 87. Again, your numbers are a little bit different for your ellipse. Same formulas. First, I will subtract. So go ahead, find your numbers. Again, those two values that you get are your F and your D. And there is my final. Again, I'm going to those 3 decimals. Okay? So now when I compare my 2 eccentricities, what I'm looking at is how those orbits differentiate or deviate from a perfect circle. So because I can see that my first ellipse is the smaller number, that's a low eccentricity, I'm just going to draw a little circle right here to remind me that that one's a little more circular versus my second is a little bigger. I'm going to elongate that one and draw it a little bit more elliptical just to get that visual. Okay? So that is my eccentricity calculation. It's fairly simple with these 3 formulas. You're always going to have those from me. You just have to be able to find the data and go ahead and plug it in. Okay? So here's your task for the rest of part 2, is we want to calculate out some eccentricities of other objects in our solar system. All right, now there are a fair amount of calculations here, but they're all going to be consistent. The first column is a subtraction, the second column is an addition, and then that third column is simply taking 1 divided by 2. Okay, every time you can round to that third decimal place. I would recommend going across this way just to be consistent. And then you're always going to make sure that your number is accurate, right? If you're getting a number like 10.75, that's not going to be accurate. Those eccentricity numbers have to be between 0 and 0.999. Okay, I'm never going to get an elliptical eccentricity that's 1, because 1 means it's actually a straight line. It doesn't circle back. So I'm never going to get all the way to 1 or above in my calculations. So once you have your calculations complete, just a few wrap-up questions down here, and then you are submitting and on your way to being ready for the homework check. Last thing is there is a video here. If you want to go through a couple more math problems with me, you can click that link, go side by side. I'll run you through a few more examples where our numbers are the same. And as always, feel free to message me if you have a question, and it's super, super helpful to give me a screenshot so you know exactly, or I know exactly, rather, where you're at. So these are our goals today. I'm looking for those submissions to be rolling into Schoology as you finish up class. You got this.